Hello there, this is Lecture G. Here in the normal full course semester length, we have 16 weeks, so this happens to be week 4 for this course. This is Lecture G. We're talking about water and solutions. So I want to spend a bit talking about water right now. Water, we all know the chemical formula is H2O, and if we look at one single molecule, which is composed of 3 atoms, it's composed of an oxygen atom here in red and two hydrogen atoms here shown in white. Okay, so we're kind of familiar with this. And it's got this interesting shape, and that gives it very peculiar properties. So water, as we know, is H2O. Now here on the planet Earth, it can exist as a solid, liquid, and a gas. On a hot, humid summer afternoon, we see evidence that there's water vapor or steam in the Earth's atmosphere, and that's water. We say if it's so wet, or it's a muggy day, or it feels sticky. That's water vapor. On a cold winter day, you can also see humidity by breathing out and seeing your breath in the air. You see your breath forming. We of course see clouds, and also if you run your car on a cold morning, you can see exhaust coming out of your tailpipe of your car, and what you're basically seeing is steam condensing. You're making clouds. Okay. So it exists as water vapor, which we call steam, and it exists as liquid, which we tend to call that just water also. And we of course know, 3/4 of the planet is covered with water, so there's a tremendous amount of water on the planet Earth. You can't live without water for a couple weeks or so. Your body will become dehydrated and you'll die, right? So our body is composed of a lot of water, and NASA and other scientists who are sending out space probes and looking through telescopes and things like that get very excited when they find liquid water on a planet or a moon in our solar system or beyond, because maybe it can harbor life, because we know here on Earth life can't exist without water. Water is needed for all living creatures. So liquid water we call water. And of course, water can exist in the solid state. In your freezer, you might have some frost formation in there. You might have some ice cubes in an ice cube tray or an ice maker. And if it snows, if you live in an environment where it snows, you can experience snow. Or even if you don't, most environments in the Earth can hail from time to time. So you have little ice crystals or ice little balls falling down in a form of precipitation, or when it's thundering really badly. Okay, so hail. So when its water is solid, we call that ice. Now, in all cases, these are water, and it's only water that we have different names for the states. Okay, so solid, liquid, gas, we call it ice, water, and steam. But that's just everyday common language for the English language. If we're talking about lead, that's solid, liquid, or gas, we would call it lead solid, liquid solid, and lead gas, or gaseous lead, for example. So we don't have different chemical names for these, and whether it's a solid, liquid, or gas, it's still water. Okay. Over on the left-hand side, we've talked about states of matter, but I want to talk a little bit more about water because it's a very unique substance, okay? In the liquid state, as you recall from our previous discussions, water is very randomly distributed, okay? So it's not all just lined up in a very three-dimensional lattice or a regular repeating thing like a solid, but there are particles of water molecules are randomly associated with one another, but they're still in close contact with each other. they can slide and slip over each other, and so that's why liquids can flow when you pour a glass of water. Now on the right we have a model showing solid water, or ice. We'll call it ice here in the video. So here's ice, and so what you'll see here is that there's a regular repeating arrangement. It looks very regular. You can see these hexagons perhaps, and you can see this is just a small fragment, okay? Ice is a three-dimensional structure. This pattern will be repeated to the left millions and millions of times, okay? It'll repeat it to the top millions and millions of times, but also in and out of the board, there's going to be a regular repeating pattern of this in all three dimensions, okay? And we're just showing like just a very small sliver there so we can kind of take a look at it. And what you'll notice is that there are spaces in this molecule. What that means is that when liquid water, which is random and more closely compacted, okay, freezes, it actually freezes by expanding its structure to create these voids within it. Okay, so there's void spaces within the ice structure as these water molecules lock themselves into place in this certain arrangement, okay, a very rigid arrangement, and it does so by expanding and becoming less dense, okay? So water here is liquid. I think you can see that on the screen. It has a density of 1 gram per milliliter. Okay, we talked about a gram, it's a unit of mass. A penny, for example, weighs about 2.5 grams. And the density of water is constant at 1 gram per milliliter. Okay, so if you measured out 1 milliliter of liquid water, it would weigh 1 gram. If you measured out 25 milliliters of water, it should weigh 25 grams. Let's see if that's true. So I'm going to do a demonstration, as I often do in the class. Okay, I've got ordinary water. Okay, there's nothing special about this other than it being distilled. Okay, ordinary water contains lots of impurities and whatnot. And I'm over here at this table. I'll position the camera here in a bit. But we've got a balance, a laboratory balance, a little bit a scale, so to speak. Let's call it a scale. And I've got this measuring device, okay? So I'm going to measure 50 milliliters of water. And this guy here measures in units of milliliters, okay? ML stands for milliliters, all right? And this balance here measures in grams. This is how we measure things in the lab. So let me see if I can find a penny. I don't have spare change in my pocket right now, but I found a penny. And let's just see if this balance weighs about 2.5 grams or so, okay? So there's a penny. Oh, wow, would you look at that? That's 2.50 grams. So it's just kind of a nice kind of round number there that I always remember. A penny is about 2.5 grams. If I want to know if my balance is working, throw a penny on there. Looks okay to me. So let's now measure this, okay? So when I use the balance here, just want to show you, you know, right now this plastic weighs all this weight, but I'm going to hit the 0 button here. And so now I'm going to fill it up with 50 milliliters of water and see if it reads 50 grams there, okay? I can't do that while I'm holding the camera. So I got another bottle of distilled water here. It's easier to hold. So we'll fill this up to the 50 mark. Okay. Might be a tad bit too high, but let's see what we get here. Okay. Put this on the balance. and this should read 50 grams, okay? It's reading 50.06 grams because nobody's perfect. I'm definitely not perfect, and there's always error that's associated with making scientific measurements, okay? So, I measured some numbers, 50 and 50, okay? So 50 grams of water has a volume of 50 milliliters of water. So 50 grams divided by 50 milliliters is 1 gram per 1 milliliter, okay? So that's a constant ratio, okay? If I have 1 milliliter of water, it's gonna weigh 1 gram. If I have 50 milliliters of water, it weighs 50 grams. If I have 100 milliliters of water, how many grams is that gonna weigh? Okay, that would be one of your homework questions. So what happens when ice freezes? When water freezes to form the solid form of water known as ice, it expands, okay? It expands and its density goes down. Point 0.9 is a lower number than 1, okay? It expands about 10%, okay? So the volume increases by 10%, which means it's less dense. The same mass is there, so if I took 50 milliliters of water or 50 grams of water and I were to freeze it, the volume would increase, okay? The volume would increase, but the mass would still be 50 grams, okay? Again, if I take 50 milliliters of water, 50 grams of water and I freeze it, it's going to be 50 grams of ice, okay? It'll be the same mass, but the volume would have increased. What that means is that ice is going to float on top of water because it's less dense. It has basically air inside of it. It's buoyant, okay? Okay, so anything less dense than water is going to float. A piece of wood, a cork, or in this case, ice, okay? Now, ice also entraps gases in it as it freezes, and that's how climatologists and paleoclimatology, all those fields, can look to see, hey, what was the Earth's atmosphere like 10,000 years ago during the last ice age, or 50,000 years ago, or 100,000 years ago? They take a special drilling rig and they drill into the ice, say in Greenland or Antarctica or something, and they pull out ice samples, okay? And the ice is still frozen, they keep it frozen, and they bring it into a special laboratory, and they melt the ice, and when the ice melts, remember again, it's gonna get more contracted, right? It's gonna compact a little bit, and it's going to release the gas that has been trapped for hundreds of thousands of years or whatever. And they have special instrumentation that can analyze the gases and see, was there more carbon dioxide or less carbon dioxide? What was the Earth's atmosphere back then, okay? So that's an interesting feature there, okay? And this is very unique to water, okay? Water is pretty much the only substance that when it freezes, it expands. The solid form is less dense, so it floats on top of the liquid form. Wax, for example, does not. I don't have these videos anymore, but if you look at how to make a candle, you take a bunch of wax and you melt it, okay? Or if you're making preserves or jellies or something at home, you know that you pour wax onto the top of the jar to seal it. That's one of the methods of making jelly, for example, home canning procedure. And if you take wax and you melt it, what you'll notice is that the last bits of wax that need to dissolve on the hot pot on your stove or whatever are sunken, okay? So there's all this liquid wax on top of it, and then the solid wax is on the bottom, okay? Ice is not that way. If you were to take a huge chunk of snow from outside, for example, and start melting it, you would see the reverse. You would see liquid water on the bottom, and then you'd see some ice cubes floating in there, okay? So ice is very strange. Now, what about the physical properties? We've talked about before about measuring the temperature of different substances using what's called a thermometer. Okay. In Unit 1, we talked about the metric units and making sure everything had a standard and everything. And the temperature is no different, okay? So if I feel somebody's forehead, you feel hot, or you feel cold, or it feels hot today. I mean, how hot, you know? So we use the Celsius temperature scale, and it's based off of the melting point and boiling points of water, okay? So if you take ice, all right, you put it in a little beaker or a glassware of some type, and you melt it, okay? These are ice cubes, here's some water. The temperature is gonna read 0 Celsius, okay? 0 degrees Celsius. So that's the definition for the 0 point on the Celsius scale. And the rationale for this is that water is a very common, inexpensive substance, and anybody in different countries can obtain it and dunk a thermometer into it, and they can get a Sharpie or something, and then, okay, this is the temperature, okay? Inside of the thermometer is a small bit of mercury or colored alcohol in this case. Okay, so down here is a bulb of alcohol. That's the red color, it has a dye in there. And there's a thin little tube inside of this thermometer that goes all the way, you know, to the top here. And if this substance warms up, it expands a little bit. And when it expands, this little red line goes up. Okay, that's how a thermometer works. And if you cool this down, the red line will go down a little bit. Now, the alcohol does not freeze at 0 degrees Celsius. We don't want to use water in this bulb because if it freezes, it'll expand and shatter the glass. So we use alcohol, which has a much lower freezing point. I can put this into a standard freezer there and it won't freeze. You can see how the lowest scale on this thermometer goes down to minus 20 degrees Celsius. Let me see, where is it? Right here. Hard to position this thermometer so you can see it, but there's a 20 with a line over it. That's a minus sign, okay? So your freezer might be minus 10 degrees Celsius or so. During a winter storm or something, you might have temperatures below 0, okay, below freezing, okay? But the 0 degrees Celsius is the freezing point, okay? So when someone says it's freezing outside, they are referring to 0 degrees Celsius and no other temperature. If it's -1 or -2 degrees Celsius, they really can't say it's freezing outside. That's just a colloquial expression meaning, oh, it's super cold. But the freezing point is that single point and no other points, okay? Ice will remain solid below 0 degrees Celsius, okay? Minus 10 in your freezer, it's gonna be ice, and at 0 degrees Celsius, water can also be in the ice solid form, okay? The symbol 0 with that little degree symbol, and then the Celsius means degrees Celsius. Okay, so that small little circle up on top means degrees. And Celsius refers to that capital C. Okay, so those are the units. Now, if you take water, you boil it at a much higher temperature, bubbles there. We know what it looks like when you boil something. You see this bubbling of stuff, right? So let's talk about what these bubbles are. These bubbles are steam. Steam is water that's in the gaseous form. Okay, that's H2O gas that's coming out. Okay, it can bubble up, it can evaporate or boil off the top and the bottom of the pot and even the sides. Okay, so that's the boiling process. In the rest of the liquid, you have very hot water that's liquid. Okay, and of course you have steam that's coming off. But the thermometer is placed into the liquid of the boiling water, and that's going to read 100 degrees Celsius. That's the definition of the boiling point of water, and that's the 100 point of your thermometer, okay? So the process for making a thermometer back in the day was to take just your mercury-filled thermometer with no markings at all in there. You put it in ice water and you make a big mark on it. And if you can, mark it with a 0. And then you put it in boiling water. And then it goes way up towards the top somewhere. And you mark that as 100, okay? And then you put on your fine needle working glasses or whatever. And you put it down on the tabletop, and then you scratch equal divisions of 100 degrees. And that's a degree or a scale, right? That's how you create the scale. So it's kind of like a ruler, okay? Then you take your ruler or whatever, and then you make 100 little marks, okay? And then, for example, if you grab your thermometer and then you read what the room temperature is, and it says, oh, it's 21 degrees Celsius, that's the temperature of the day, okay? So well, I don't think you can see red very well on the video, but let me go ahead and do it anyway. Here's your red alcohol, and that line might come up to 23 degrees or 21 or something. So that's about room temperature. Okay. Can you see that on the video okay? Yeah, so I'll stop using red after this, but 20 degrees Celsius is about room temperature. Not 0, it's not 100, it's around the 20, so it's a lot closer to 0 than it is to 100, okay? All right, we of course in the English system use Fahrenheit. I won't go into how to convert these to Fahrenheit or anything like that, okay? Because we're focusing on the metric system. So that's a little bit about water. Let's review. It freezes or melts at 0 degrees Celsius. It boils at 100 degrees Celsius. On the planet Earth, it can exist as solid, liquid, or gas, and it expands in the solid state. So as you're going from liquid to solid, we call that process freezing. And when that physical change occurs, ice is going to expand out and get less dense, okay? The density of water, as I demonstrated with the balance, is 1, okay? So 1 gram will weigh 1 milliliter of water. You should memorize the number 1 and remember that that is based on water, okay? And also memorize 0 and 100. There's 2 different temperatures that the Celsius temperature is based on, okay? Now, I had talked about how water is critical for life to function, and that's not just because of the water by itself, but it's because of solutions, okay? A solution is defined as a homogeneous mixture of 2 different substances. The substance in greater amount is always going to be called the solvent. doesn't matter what this is, solid, liquid, or gas, if it's present in greater amount, it's the solvent. Greater amount might be defined based on volume or mass, for example, okay? The substance in lesser amount is called the solute. Okay, so those are some key vocabulary words to write down. And then the solution is the mixture of those two, the homogeneous mixture of those two, okay? So memorize the term solution, memorize the term solvent, and memorize the term solute, okay? Let's look at some examples of solutions before we talk, again, much more about water solutions, okay? Now, there's many different types of solutions. As I mentioned, some are gaseous, some are liquid, and some are solid. And there's a bunch of different examples, and we'll talk about the solvent and the solute in each of those cases, okay? So let's start by making a summary table here. On the left, we'll have type of solution. We'll talk about an example of the solution, and we'll talk about the solute and the solvent. Okay. First off, let's talk about a gas. There's many different types of gas mixtures used in welding, medicine, scuba diving, but let's just talk about the air since we're very familiar with that, okay? Air contains, let's just think about the two primary substances. Air contains 80% nitrogen and 20% oxygen, and I'm greatly oversimplifying the smaller quantities in there, but the primary solvent here is going to be nitrogen because that's present as 80% of the air. Now there's a bunch of stuff in air. We even talked about water vapor, but I'm going to talk about oxygen being a solute. And as I've mentioned with homogeneous solutions, they are not needing to be mixed because they are uniform throughout. So each morning when I come into this classroom, I know that there's oxygen that my students need to breathe, and there's nitrogen in here as well. I don't get the broom and stir the air in this room because it's uniform throughout. Okay, that's what homogeneous means. So I can breathe just as well in the back of the classroom as the front left of the classroom. Let's talk about liquids. Well, there's many different kinds of liquid solutions. You can have solids dissolved in liquids, you can have gases dissolved in liquids, and you can have other liquids dissolved in liquids, okay? So let's talk about a gas dissolved in liquid, and let's talk about soda, okay, soda. A soda pop, you know, a carbonated beverage like Pepsi, right? When you open it and you pour it into a glass, you see these bubbles start coming out. Those are bubbles of carbon dioxide. And they bubble out of water. Okay, so that's a very common, you know, observation that we can make of a soda pop. Next time you pour it, just look at the bubbles and just be thinking, oh wow, that's a lot of little bubbles of carbon dioxide coming out of that homogeneous solution. There's a lot of stuff in there, caramel, coloring, sugar, caffeine probably, but we're just focusing on carbon dioxide here as a gas. Liquids can also dissolve in liquids. One of those examples is vinegar, okay? Vinegar is a liquid, as acetic acid technically is the acid that's in vinegar, but this is a 5% solution. Okay, if you look really carefully, you got to hunt around for it. You can see that vinegar is a 5% solution of something called glacial acetic acid or acetic acid in water. Okay, so vinegar, let's write down here, liquid in liquid. Alcoholic beverages as well is something I could talk about, but I don't want to always be talking about alcohol in the class. So vinegar, I'll even put a 5% there. Oftentimes for solutions you see percents on the labels. 5.25% bleach, 5% vinegar, 3% hydrogen peroxide, something like that. Okay, so percents mean it's a clue that it's not pure. Okay, it's not 100% something, it's not a pure substance. It's a mixture if you see a percent ever, okay? That's a kind of a hint for you to look for. So this is going to be acetic acid. And that's going to be dissolved in water, okay? I don't want to waste time going to the back stock room and getting some acetic acid so you can see what it looks like. It's just a liquid and it's in a glass jar. That's acetic acid. And water we know is liquid water. But if you mix the two together, you just get a liquid solution. And it's homogeneous, okay? If you're using vinegar for cleaning or for pickling or something, you don't have to shake this up before you use it because it's uniform throughout. It's homogeneous, okay? Solids can also dissolve in liquids. Example of that might be household bleach or seawater. Bleach contains a complicated sounding chemical called sodium hypochlorite. That's the chemical that bleaches clothes and removes stains. And it's dissolved in water. On the bottle, you have extra strength bleach that might be 6% or 7% or whatever. And you might have standard bleach, which is 5.25% or whatever. So that's an example of a solid dissolved in a liquid. So sorry, these have some complicated chemical names. You don't need to memorize those, other than carbon dioxide, I think, which is very, very common for our breathing and stuff. But these are just examples that we can relate to, okay? Bleach, vinegar, and a soda can. Sometimes you have a solid, sometimes you have a liquid, sometimes you have a gas dissolved into water, okay? The next type of substance is a solid dissolved in a solid. And we typically call those alloys. If we are talking about metals, okay, so two different metals dissolved into one another are called an alloy. And so let's just talk about brass. Brass is a mixture of zinc and solid. You have different varieties of brass, but the major component is going to be copper. Okay. The minor component is going to be called zinc. So again, remember the term solute. It means the substance in lesser amount, and solvent is the substance in greater amount. So for example, if I had 25 grams of zinc and 75 grams of copper, which one of these would be the solvent? Well, that's a bigger number, so that's the solvent, okay? And the two together would be a mixture, and we call that mixture brass. Brass can be commonly found on your, keychains, okay? Keychains. So, like a key like this is brass, okay? It's a strong metal, good for making keys. They don't deform easily, and they resist corrosion, and there's all kinds of properties that are useful for that, okay? All right, now the major type of solution we are going to be talking about in this class is water, okay? Water is a very useful solvent, okay? But first we have to talk about what dissolves in water. We know a copper penny, if you put it into water, it doesn't dissolve. If you put salt into water, it does dissolve. If you put sugar in water, it does dissolve. But other things don't dissolve in water, right? Sometimes you're cleaning a stain and it's, you wash your clothes and you're like, oh man, that stain didn't come out. That means it did not dissolve into water to make a solution for it to be washed away during the rinse cycle of your laundry machine, okay? So let's talk about the formation of solutions, and it's a very simple idea. Like dissolves like. Okay. Like dissolves like. So what this means is that because of the interaction between the particles, if a substance has a characteristic we call polar, it'll dissolve other things that are polar, okay? So what is this word polar? Well, it would take too long to explain and we don't need to really analyze it, but let me just give you some examples of this, okay? So water has this chemical formula, and alcohols have a similar chemical formula. And again, I just want to make this very trivial and come back to this, this phrase, like dissolves like. And if you look at the water molecule, it contains oxygen. And if you look at alcohols, they also contain oxygen, okay? So for the purposes of this class, all you need to do is look at the chemical formula to see if it is similar to the water molecule, okay? Alcohols have what are called hydroxyl groups, and water has hydroxyl groups. They're both polar and can do hydrogen bonding, and they have favorable solute-solvent interactions for the two to dissolve to make a homogeneous solution. There's a lot of theory and all that, but what you basically need to do at the end of the day is look at the chemical formula, and if it has oxygen, it'll dissolve in water, okay? So things like alcohol, things like methanol will dissolve, things like ethanol will dissolve, and things like sugar will dissolve. Yeah, so I'll just put one of those there. This is sugar, and so what you're going to be looking for, of course, is, oh, okay, there's oxygen in the chemical formula. And we all know intuitively that sugar dissolves in water. And so we can just kind of, at first glance, make the hypothesis that, well, things that contain oxygen are going to dissolve in water, okay? Good so far. Now, what about grease or oil or something? Well, hold on. There is one other class of compounds that will generally dissolve in water, okay? So we've talked about alcohols or sugar, and it turns out that salts are polar because of the charges that they contain, okay? So that would be another example. Salts generally dissolve in water. So what's a salt? Table salt is this chemical here, sodium chloride. And what you'll want to do is take your periodic table and look to see where these elements are located. Sodium is a metal that's located on the left of the periodic table, and chlorine is a non-metal located on the right of the periodic table. And that's what we call an ionic compound, okay? So sodium is a metal, chlorine is a non-metal, and please review your notes that you've taken on the previous videos. We use the staircase in the periodic table to make that determination, okay? Let's look at another salt. Calcium chloride is a white crystalline substance. We throw it on the ground to melt the ice or melt the snow on our driveways and walkways and the roads and all of this, okay? And it also dissolves into water. And if you look at the chemical formulas here, capital C, lowercase a stands for calcium. That's a metal. And we already know that chlorine is a non-metal. Okay? So if you have this interesting combination in your chemical formula of a metal and a non-metal, we can identify that substance as a salt. Okay, there's many salts besides just table salt. There's sea salt, and there's many other different kinds of minerals that we call salts. So these generally will dissolve in water, okay? So we saw polar will dissolve polar, and we can look at the oxygens in two formulas and go, oh yeah, those are going to be compatible. And we can see a salt, and we can say, okay, that's polar, it's going to dissolve in water, okay? So we talked about methanol and water, okay? They both contain oxygen. We talked about salts and water. Salts are an ionic compound, metal, non-metal combination, okay? Non-polar things will dissolve non-polar things, okay? This is situation number 2. We won't talk too much more about this because water's polar, and so we want to talk a lot more about water. But if you want to dissolve butter off of your clothing or grease from a motorcycle chain or something like that, you're going to use kerosene, right? Or you're going to use gasoline or some kind of degreaser. So those are non-polar things, okay? So let's look at these two chemicals. Let's not name these or talk about the names, but this first chemical here is a hydrocarbon. Hydrocarbons are chemicals composed of hydrogen and carbon. This chemical right here, okay, I'll tell you what the name is for that. That's gasoline. Octane gets its name from the number of carbons it contains. And that's also a hydrocarbon. Hydrocarbons are composed of only hydrogen and carbon. And again, like dissolves like. So let's just treat this very trivially. Well, that guy right there just has carbon and hydrogen only, and that guy right there has carbon and hydrogen only. So they're going to dissolve one another and be compatible, okay? Because of the like dissolves like principle. Okay, so these two will make a nice solution. So like dissolves like, we have two possibilities. We have polar and polar. Okay, we talked about water and alcohols, water and salt. And then we have nonpolar and nonpolar. We talked about two hydrocarbons that, because of their similar formulas, are compatible with one another. Now this is not like dissolves like, because these are not like each other. They're opposites. An example of this would be like oil and water. Okay. The formula for like olive oil, even olive oil, which is kind of a simple thing, is a very complicated chemical formula, and it might confuse some students. So I'm just going to use the vocabulary word here. Everybody knows that oil does not dissolve in water. If you have vinaigrette salad dressing, you know that you have to shake that thing up before you can dispense it onto your salad, okay? If you're cooking soups, maybe you're simmering some broth from some beef or something like that, and you can see these oil droplets on the top of your soup, right? And on and on and on and on, okay? So oil and water don't mix. And that's because they're dissimilar. They are not like each other, okay? So that's how you can predict if you're going to have a solution or not. Let's kind of take a look at some problems here before we go onwards. So identify the solute and the solvent, okay? So let's just do two. I think you'll get the idea of things as we go through. Okay, so here we have 3 grams of this chemical, which is called hydrogen peroxide, and 97 grams of, we know that chemical, that's called water. Okay, so when you look at these, you look for the lesser amount. The lesser amount is the solute. The larger amount is called the solvent. So when it says identify, you know, that's going to be the name of your chemical formula, okay? So in this top example, water is the solvent and hydrogen peroxide is the solute. And normally you buy these at CVS or Walgreens or whatever, or Walmart or wherever, anywhere. You look on the pharmacy aisle and you have 3% hydrogen peroxide, okay? And that's used for disinfecting wounds. Maybe a diluted solution of that's used for gargling or removing stains and some other applications. Next up, we have capital C, lowercase u, that's copper. Capital A, smaller case u, that's gold. Okay, so this is an alloy, copper and gold. And so we want to look at the numbers, 13.2 versus 3.7. 13.2 is a bigger number. So that's going to be the solvent. The solvent is copper. And over here, this is present in lesser amount. So the solute is gold. Okay, the solute is gold. All right, we know that, we're good, okay? All right, next up, we want to identify which will dissolve. All right, let's just do one of these problems. I think after this, you'll get the idea of what you need to answer. So, which of these substances are going to dissolve in hexane? Hexane is nonpolar, okay? So we got vegetable oil, which is nonpolar. That's going to dissolve because nonpolar and nonpolar things are compatible and will mix because like dissolves like. How about iodine? This substance here is nonpolar, okay? So nonpolar, nonpolar. Okay, iodine is also going to dissolve into hexane, okay? How about lithium chloride? Lithium chloride is ionic. It's a salt, okay? So you need to think backwards. That's a salt, and we're saying that that's going to be considered to be polar, okay? We never really say a salt is polar. I might say that, you know, just kind of like by mistake or something. But lithium chloride is polar. Okay, so that's dissimilar. So not that one. Lithium chloride is a salt. Lithium is a metal. Chloride or chlorine is a non-metal, so that's a salt, and it's not going to dissolve into water. Into hexane. How about water? Polar and non-polar. Okay, that's dissimilar as well. So it's just these two choices here. Okay. Now let's talk about the properties of solutions. Okay. So what I want to talk about, I'm going to do a little demonstration here, and then I'll show you just a nice little figure from the textbook. But I want to talk about electrolytes. Okay. Now, you've heard the term of electrolytes from sports commercials, drinking Gatorade or something like that. You know, when your body sweats, the liquid that is called sweat contains salts, okay? Your sweat will taste salty, or if you're really working out hard and like somewhere, you'll actually deposit salt on your face. The electrolytes conduct electricity, okay? And we want to look at a couple different compounds here to see what is going on, okay? Now, I've got this very dangerous piece of apparatus to measure conductivity. I've got a plug here that I plug into the outlet, okay? And these two wires are not connected, okay? If I were to tie these or twist these together and plug this in, this light bulb would light up. But right now, these are not connected to each other, so they won't light up, okay? So the plan is that I'm gonna put some water into these different containers, and then I'm going to put this in here. And if the light bulb lights up, we call it an electrolyte because the solution itself can conduct electricity. And if I put this in here and it does not light up, I'm going to call it a non-electrolyte because the solution does not conduct electricity. Okay? So let me go ahead and do this. Again, we're using distilled water that contains no ions. It's just very pure water. And I'm going to put water into this first guy here. Fill it up quite a ways so that the electrodes from that light bulb can reach down into the solution. Okay. And this one I have just this glass stirring rod so I can stir up the solution. Of course I don't want to use metal here. I'll electrocute myself. Okay. Now I have two different well, I'm going to test pure water so I can show you what that looks like. And then I've got a couple of different items, okay? I've got sodium chloride here, okay? And I'm going to put that into this guy right here in the middle, okay? So I'm going to put some salt in there, and we'll just, stir that up a bit, okay? In this third test tube closest to the camera, I'm going to be placing sucrose. This is a fancy name, it just means table sugar. Okay, So I'm going to put some table sugar in here, okay? Kind of like confectionery sugar with very large crystals. So I'm going to grab a different stirring rod and stir that up a bit. All right. Move some equipment to the side here so we can take a look at these. I'll move the camera back a ways so possibly you could see me at the same time I'm doing this. All right. So we've got water right here. We've got sodium chloride or salt that I put into here, and I've got sugar that I put into this water here. Now, if you look carefully in the video, you'll see some solid on the bottom. It hasn't completely dissolved yet, but we'll get the data we need, okay? So I'm going to plug this in. If I touch these, I'm going to electrocute myself, okay? So I'm going to first put this into water, and there is no action here with the light bulb. It's off. So we say that pure water is a non-electrolyte. Next, I'm going to put this into here, and the light bulb, of course, lights up. You can see that in the video kind of nicely. It's pretty bright for me. What this means is that a solution of sodium chloride and water or salt water is an electrolyte. It conducts electricity, okay? I just put this back into pure water to maybe wash those electrodes off. And now we're gonna put this into sugar water. If you put this into water, the light bulb seems to be off here, okay? So we say that sugar water is a non-electrolyte. Okay, so let's test sodium chloride back again, on. Let's test pure water, off. Okay, so we can see that it's only sodium chloride that lights the light bulb, but water is a non-electrolyte and sugar water is a non-electrolyte. I'm out of time right now for this video, but we'll look and classify electrolytes and non-electrolytes based on their chemical formulas. Okay, it's a very interesting property of water-containing solutions. As always, thank you very much for watching my YouTube videos. Please give a like and a thumbs up, and please consider subscribing. Have a nice day.